Hello, everyone. My name is Kajtaz Bllaca and come from University of Prishtina, Kosovo. First, I would like to thank the organizer for giving me opportunity to talk in this conference. My talk is about the bounding the order of some special zeros of functions in the Selberg class. So first, I will talk about the motivation, the behavior of L functions in the critical strip. Received a lot of attention since the first proof of the prime number theory. And the special zeros of these L functions carry relevant arithmetic or geometric information on the objects that were used to define this L functions, also zeta functions. Especially the value at the central point S, which is equal half of various families of L functions, zeta function is very important and is subject of intensive study of this. Explicit formulas now they have this relation between analytic and properties of zeta and L function and the geometric, algebraic, and etc. properties of the object to which the function is associated. First explicit formulas showed in the works of Riemann and von Mangold. The most famous of this formula is obtained by von Mangold, which is this explicit formula. The sum on the left side is taken over the prime powers, and the sum in the right side is taken over the non-trivial zeros of Riemann zeta function. This explicit formulas motivated Omar in his paper to study the multiplicity of the eventual zeros of the Dedekind zeta function of a number field K. Also, he proved the asymptotic formula for the multiplicity of the eventual zero at the central point, and he gave the location of the first zero with positive imaginary part, assuming the generalized Riemann hypothesis. In 2010 and in 2011, Leyla Smailovic and his co-worker Almas Aojak, they proved the explicit formula for function in the Selberg class and its generalization. And this explicit formula motivates me to do the similar result as Omar did for the Dedekind zeta function. So first, now I will give the definition of the Selberg class. In 1989, Selberg defined the general class of Dirli series having an Euler product, analytic continuation, functional equation of Riemann type, and the definition of such class is denoted by S and consists of the Dirli series, which are of this form and satisfies the following 5 axioms. So they can represent it as a Dirli series. They have analytic continuation. They satisfy functional equation, also Ramanujan hypothesis, and they can represent it as a Euler product. Some examples of members of Selberg class are the Riemann zeta function, Dirli L functions, Dedekind zeta function, Hecke L functions, and etc. Now I will give the definition of the extended Selberg class, which we denote by S sharp, which is class of functions of the Selberg class, but satisfying only the 3 first axioms. And it believed that this class, this L sharp, contains all the L functions which are of interest in the number theory. It means that this contains the class of Selberg class. And in their paper, Ojak and Smailovic introduced a new class of function which they they signed with the S sharp flat, and this class is satisfying axiom 1 and 2 of the Selberg class, and this two following axioms. So the functional equation that satisfies Selberg's lemma, it's some of different functional equation, because now the mu coefficient satisfy this conditions. Also, now the logarithmic derivative of the functions can possess a de Riemann series representations. I will skip this invariance, just to mention that this invariance that is conjecture, it's important in our result. So the crucial tool for deriving our main result is the explicit formula for function in Selberg class and its generalization applied to suitable constructed test functions. This is the explicit formula, the theorem 1, for the regularized function satisfying these three conditions. Then this formula holds true. This is the explicit formula for function in the Selberg class S sharp flat. Now, if G is even regularized function, this is the explicit formula for satisfying when the G is even function. This explicit formula enables us, assuming the generalized Riemann hypothesis, to give a multiplicity of the order of the central point and provide an upper bound, and for the first zero, which is different, the imaginary part is different from zero. So this is our main result, but to get our main result, we need some lemmas. And our test function is this. The G function now is our test function to prove our main result, which is satisfy this condition. So this G function now is even function. And assuming a generalized Riemann hypothesis, we prove that the multiplicity of the eventual zero at the central point of function who is belong to the class S sharp flat, where the real part of the coefficients of that are greater than zero, and this constant is invariant, and the conductor of which, if conductor is greater than E, then R is less or equal with this. So this R is multiplicity of the eventual zero at the central point. If QF is less than E, then we have this bound, which with W we denote the Lambert function. And as a consequence of this theorem, we have the following corollary: if F belongs to the class S sharp flat, when with the real part of the coefficient CF are greater than zero, also assuming that conductor QF or F is less than or equal to E, and F is holomorphic, then F on a central point is different from zero, so it's non-vanishing at the central point. So it's not satisfying the Riemann hypothesis. Now, as an application of our main result is that the automorphic L functions, since they are belonging to the class S C sharp, when we can get the results of the theorem 2 in the following corollary. So now the R is the multiplicity of the eventual zero central point, but now for the automorphic L automorphic function. Now, the second, our main result is the location of the first zero with positive imaginary part. In this section, we provide an upper bound for the height of the first zero, which is different, the different imaginary part is different from zero. So if we let denote the h by the height of the first zero with imaginary part with different from zero, then the function belongs to the class S sharp flat, assuming that f satisfies also axiom 5 that can be represented as an Euler product of the Selberg class, and the real part of this coefficients are greater than zero. Then we have this bound for the upper bound for the height of the first zero. Also, if we can have another result, if this height for the height of the first zero, if f belongs to the Selberg class, if in the case that f belongs to the Selberg class, but also f from 1 plus et is different from zero. So that this condition is equivalently with the prime number theorem for the functions in the Selberg class. So if the f is now belongs to the Selberg class and satisfies this condition, the bound for the height of the first zero with imaginary part different from zero is, we can write it like this. So it's maximum of these two expressions. Also
you have 1 minute.
We can apply this results at our automorphic L functions for the height of the first zero and for the function LSP. And this is references I used. And thank you.
Thank you.